Hello children, do you remember what we have learned about extrinsic semiconductors? Let us take a recap. What are the two types of extrinsic semiconductors? We know they are P-type semiconductors and N-type semiconductors. So in order to draw the P-type semiconductor and N-type semiconductor schematically, what we can do, that is what we are going to study, and also we have to study the energy band diagram of P-type semiconductor and N-type semiconductor in this session. So let us go. In a P-type semiconductor, what is the dopant called? It's called the acceptor, right? So it accepts an electron which was not its own. So how will you draw a P-type semiconductor? So listen children, a P-type semiconductor is looking like this. So there are spaced atomic cores. You know, the P-type semiconductor, the atom is holding an electron. The atom which was neutral is holding an electron which is not theirs. So that was, they were called as acceptors. So when they take an electron, atom being neutral, what should be the representation on the atomic core of a P-type dopant? So what is it? It will be, the dopants will be represented by negative. Usually children always make a mistake that if it is P-type, they draw positive. No, it is wrong children. The thing is that in a P-type semiconductor, the dopant become an acceptor and the neutral atom receives an electron somewhere from the lattice of silicon. So neutral plus an electron, they will become a negative charge and they will produce a hole somewhere in the crystal when they accept an electron. So associated with every negative core of a trivalent impurity, there must be a hole. So what must be the representation of a P-type semiconductor? All the donor acceptors must be marked as negative and a hole is associated with it. So this is the legend of a P-type semiconductor. So how will you draw an N-type semiconductor, children? How we have produced this N-type semiconductor? Do you remember it? Yes, by adding a pentavalent impurity. And 4 electrons were used to bond with the other silicon atoms. But the pentavalent impurity now is having a 1 electron less. An atom with 1 electron less should be always positive. And it has donated its electron to the crystal structure. So how will you represent an N-type semiconductor? What is the legend of an N-type semiconductor? It will be positive donor cores. Why positive, children? Because they have donated its electron. A neutral atom minus an electron is always positive, and one of the electron has been contributed from each donor atom to conduct inside the crystal. So this is the legend of a P-type semiconductor and an N-type semiconductor. Continuing with, how will we write the equation for the carrier concentration of an extrinsic semiconductor? It can be written as an extrinsic semiconductor consists of electrons as well as holes, and it is equal to Ni intrinsic square. You have to understand, this can be asked for numerical analysis. Number of electrons into number of holes is equal to number of intrinsic concentration, number of intrinsic charge carriers square. This is an equation dealing with the charge concentration in an extrinsic semiconductor. Continuing with, let us go to the band gap diagram of a P-type semiconductor and an N-type semiconductor. Listen children, we are going to draw the band gap, and you already know what is the y-axis. Increasing energy, we have drawn already in the previous classes, that is increasing energy. And what are the two types of bands? Just remember, yes, the valence band and the conduction band. And we know there is a valence band here and there is the conduction band here. So while we study this, children, We can associate this to the general human psychology. What is it? In our life, there are donors and acceptors, right? So when we meet some acceptors, we always tell that their mental level is too low because they always want to accept something from others. They are not ready to give. So here also, as humans, if they are acceptors, their mental level will be too low. That they always need emotional security like that, isn't it? So in a p-type semiconductor, it is an acceptor atom. So the acceptor level must be drawn too low near the valence band because they have to receive their electron from the valence band, right? So where is the acceptor level situated? You can just draw by remembering the example that I have given you. So what is it? This is our acceptor level, and the acceptor level has to accept something. It has to take electrons from the valence band, and this acceptor level or energy level should lie, the acceptor energy level should be lying very close to the valence band, and it must be of the order of 0. This difference must be of the order of 0.01 electron volt to 0.05 electron volt. Just understand, the acceptor level must be very close to the valence band. And we know this valence band consists of what? This valence band is having. The conduction band will be having one electron here because of the temperature generated charge carriers, and instead that there will be some hole here. That is it, that is correct. But we know that in a p-type semiconductor, the holes are the majority carriers, right? This acceptor has taken so many electrons to form their bond, so that the number of holes, here there are electrons also, surely there are electrons also, but whenever an acceptor is taking the electrons from the valence band of silicon, what happens is that this valence band will contain more holes than the electrons present. Look, there are more holes should be present. In conduction band also there will be electrons because Ne is equal to NH in an intrinsic semiconductor, and they are intrinsically thermally generated charge carriers. But the holes here, why there are so many holes here? The acceptors has taken its electron back to form the bond, so that more holes are formed in the valence band. Here you have to understand that holes are always found in the valence band. You should not draw holes in the conduction band. So moving on to the band gap diagram of the, so what is this called, children? What is this gap called? This is called the forbidden energy gap, and it is called EG, right? And moving on to the band gap diagram of, in your textbook it is clearly given that in the textbook it is 14.9, figure 14.9 explains everything. And in the case of an n-type semiconductor, here also there is an increasing energy. And what is the peculiarity of an n-type semiconductor, children? It consists of donors. So we know in human beings also, when they are donors, their mental level will be too high, right? So to give something, our mental level should be too high. So like that, if there is a conduction band here, and here there is a valence band here, this is the valence band and this is the conduction band, you can draw. And the valence band will consist of, what is it? Electrons. Electrons are there, so many electrons are there in the valence band, and they are not ready for conduction because they should gain some energy. And there may be some holes also here. There may be some holes also here. Why? This hole here in the valence band, because they are intrinsically generated charge carriers. That is, they are thermally generated charge carriers. Where should the donor level lie? As it is a donor, it should be of the higher level. It should give its electron to the conduction band, children. It should readily give their electron for conduction. So where should the energy level of a donor lie? It should lie near the conduction band. Their level is always high. This is E donor, and the level difference between the conduction band must be approximately of the order of 0.01 electron volt, so that the donor can give its electron to the conduction band. So how many electrons are there in the valence band? So so many electrons, more than that, so many electrons can be drawn in the conduction band because it is full of charge carriers given by the donor. So here children, we understand that the number of holes is greater than the number of electrons in the conduction band. Here the number of electrons in the conduction band is greater than the number of holes, and of course this gap is called the forbidden energy gap. Before summing up, there are certain things to be noted once again children. The valence band is only at the lower level. First point, the conduction band at the upper level. And holes are always found in the valence band. You should not draw any holes here. Holes should be always in the valence band. In a p-type semiconductor, the number of holes here should be more. Here the number of electrons should be more in the conduction band of an n-type semiconductor. Acceptor level, acceptor takes the electron from the valence band, so the acceptor level should be close to the valence band, but the donor gives its electron. It is having a higher level of energy, so that the donor level must lie close to the conduction band. Children, these two equations is a sure question for your board examination, so draw it. The drawing is a skill with all the necessary markings. Study it for a 3-mark question. Hope you have understood it and you will focus on it and draw it well. Thank you.